Hey, welcome to 7.4 Logarithms. Here we go again. Okay, I gave up on the Mobi because the pen hates me and it wasn't writing properly. So this is going to look a little different than the teacher notes that are in Canvas. The teacher notes actually have my handwriting on them. This one I typed stuff in, so not quite as great. We are going to do all of 7.4 today. So hang on to your hats. We usually take 2 days to do this. We're going to go through product property, quotient property, power property, and talk about change of base formula. And we're also going to talk about simplifying or expanding logarithms. Lots to do today. Let's get started. Okay, let's remember what logs are. Logs are inverse operations. If you have a variable that is an exponent, how do you solve for it? Other than check and guess or graphing, you need some sort of algorithm to solve for it. And that's where logs come in. So we have 3 examples here. And what I've done is I've just put them here. I am going to get rid of me because, I'm just taking up space right here. So let's get rid of me there. And let's keep going. Okay, first logarithm expression. It was log base 2 of 4. Now, if you do not have the note sheet printed out, that's totally fine. Grab a piece of scratch paper and let's just work on these. We went ahead and did this in 7.3. So this should feel like review. Remember, we take the base. 2 is the base. Base to the exponent. Remember, the exponent is its own side of the equation. And that equals the argument. And I made kind of some swishy arrow things when I did that. So 2 to the x equals 4. And you can see that written out over here. So your exponent, which was kind of a rock star, it had its own side of the equation, now is written in its proper form when you're in exponent form. Now you need to look at the equation. 2 to what power equals 4? And we know the answer is 2. 2 squared equals 4. Here's another one. Log base 2 of 2. What does that equal? Well, first thing I do is set it equal to x. When I have to evaluate these things, I set them equal to x, and then I change them to exponent form. So here we go. Our base is 2. 2 to the x power. Here's the x. And we're going to set that equal to the argument. And you can see I did that right over here. Now, take a look. 2 to some power x equals 2. And we talked about this back in 7.3. That answer is 1. Now, more generically, if you have a log of some base, b, of some argument a, what does that equal? Well, it equals your exponent. To put that into exponent form, your base to your exponent equals your argument. Now, again, this is review. We did this in 7.3. What's new in 7.4 is all the log properties. Now, if we were in normal time and I was able to work through these more slowly with you, we would develop 1 or 2 of these formulas. So you can see that it's not like some sort of mathematical wizardry where I'm just kind of waving my wand and presto, here's now a formula that magically works. These are actually derived from real log properties. And I put the first derivation in the notes. You can kind of scroll through this and take a look at it. The teacher notes, let me get rid of this. The teacher notes also have information in them as well. So these are not just made up, or they're just not like some whimsical thing that somebody came up with. They're actually real derivations. The proofs of them are there. Any math textbook has them. You can Google them, whatever. So they're real things is what I'm trying to get at. Okay, so product property. This says if you have the 2 separate logs, same base, note they have to have the exact same base. The 2 log expressions are added together. You can combine those to a single log expression. So log base b, notice the b stays the same, by multiplying x and y, by multiplying your 2 arguments. So this allows us to take what could be conceivably several log expressions if they're all added together and combine them down to a single one. Let's take a look at how this works. Now I have log base 6 of 5 plus log base 6 of x. I want to combine those to a single log expression. So I keep the base the same. Notice it's still log. There's my 6 from those are all 6s. And then I take the 5 and the x and I multiply them together. So to simplify that expression, it becomes one expression since they're added together. And the product property says that if you have 2 log expressions added together, you can combine them into a single expression by multiplying the arguments. Okay, let's try another one. How about this one? Log base 5 of 2m plus log base 5 of 3. That now equals log base 5 of, multiply the 2 arguments, 2m times 3. Now, if you can actually multiply them, go ahead and multiply them. 3 times 2 is 6. So you'll notice over here, I went a step further and was able to combine them even more. That will happen quite a bit. Here's another example. I have log base 4 of 2 plus log base 4 of 8. Okay, my bases are the same. They're both 4. So when these are two expressions that are added, I can multiply those arguments. So I'm going to make a single log expression here. Log base 4 of the 2 times the 8. So those are written together right here. Now do the math. 2 times 8. Well, that's 16. So my expression, and I kind of want to be done right now with this, is log base 4 of 16. But wait a minute. Take a look. Remember what log expressions are. They equal an exponent. So every time you reduce it down to a single log expression, it's worth taking a look at and saying, hey, is there some exponent I can put on 4? Oops, sorry, folks. Put on 4 to make it equal 16. If you can't think of one, and there isn't one, you're done. But if you can think of one, you're not quite done yet. Let me show you what I mean. Let's take log base 4 of 16. Let's set that equal to x. Now, put this into exponent form. So you've got your base to your exponent equals your argument. 4 to the x power equals 16. Now, can you simplify that even more? Of course you can. So this entire original expression over here, log base 4 of 2 plus log base 4 of 8, actually just simplifies down to 2. Okay, yeah, this gets a little crazy. That's okay. It's kind of fun though. It's like doing puzzles. If you're a puzzle doer, you'll really enjoy this stuff. Now, if there was a product property, you can better believe there's going to be a quotient property. Mathematics is wonderful in that it works like that. Okay, so what do we do if we have two log expressions now, and instead of being added, they're being subtracted? Well, you probably rightly guessed that you combine them to a single log expression where you divide them. Now, a couple things to remember. It's always first, see the x is on top, first divided by second. So the second expression is always the denominator. It's not big over little or something like that. It is first expression. The one that's being subtracted becomes the bottom argument there. Okay, let's play with a few of these. Let's write these as a single log expression. Let me grab a screen here because this is a lot to look at. Sorry, folks. I know that's a little annoying. But I just kind of want to focus your eyes here on what I'm talking about. So say you start with log base 3 of 4. You're going to subtract log base 3 of 6. You want to write that as a single log expression. So go ahead and write log. Keep your base the same, 3. And now it's first expression divided by second one. So 4 divided by 6. So what I have is log base 3 of 4/6. And every math teacher in the world makes you simplify fractions. I am no different. So this divide top and bottom by 2 becomes log base 3 of 2/3. Try another one. Log of 10 minus log of 5. Ruh-roh. We don't have a base. What is our base if there's none written in there? Frantically look back through your notes, 7.3. If there is no base in there, it's the common base, which is 10. And you can kind of see I put it in actually over here, so I kind of gave myself away. If it helps you to squish a little 10 in there and squish a little 10 in there, go right ahead and do it. You'll never be wrong. Okay, so this is really log base 10, or just log of 10 over 5. And again, I can simplify 10 over 5 to 2. Now, there's no number I can put on 10 to make it equal 2, no exponent that's intuitively obvious right now. We will find out ways to solve this and actually reduce this for later on. But for now, we're going to leave it. Now, you are going to run into some where you cannot simplify. Take a look at this one. See if you can figure out why you can't simplify it. If you notice that one is log base 3 and one is log base 6, you're exactly right. You can't simplify these if they have different bases. And that's true with the product property, and it's true with the quotient property. If they're different bases, that's as simplified as that expression gets. You're done with it, move on. Okay, third property. We're going through these kind of quick. So here we go. Power property. We actually wind up using this one a lot when we're solving equations with logarithms. This one notes that the actual argument, the part written after log and base, might have an exponent on it. How do you handle this exponent? We actually bring it down front. And this is equivalent to saying, take that exponent, bring it down front, right out front, c times the log base b of x. This gets rid of anything that might be an exponent in our expression. The derivation of this, if you're like, wait, what are you doing now? Derivation is in your book. It shows how to work it out step by step, where this comes from. And like I said, I know Google has tons of these property proofs on them. If you want to see one in more detail, just shoot me an email. I'd be happy to send it to you. Okay, here we go. So how this works. Suppose you have a log expression and the argument has an exponent on it, and we have to simplify. The very first thing you do before you do anything else is bring all your exponents down front. So you see this 2 right here. To simplify this, you write it down in front, 2 log base 3 of 4. Now, if I could simplify this part, I would. But this says, what exponent can you put on 3 to make it equal 4? Well, I don't know of one. I mean, there is one, but it's like a fraction and it's weird. So we're just going to leave it. That's as simplified as we're going to go for now. How about this one? Log of the quantity 4x. Ooh, no base written in. So that means you have the understood base 10. If you like to put that in there, write it in there. But what we can do is take that x and bring it down right in front of the word log. So it's x times this quantity. You can write it as x log base 10 of 4 or simply x log 4. Now you can also go the other way with these. Suppose you have 4 log base 2 of x, and for some reason you need to do some simplifying or whatever. You can actually take that coefficient and, and take it and move it right back up to being an exponent. Now note it's going to be, you're going to put, if that x wasn't in parentheses, I would have put parentheses around it because that exponent will apply to everything in here. So if something is added or subtracted or there's several terms in here, this 4 would apply to all of it. Okay. Now let's talk about a special case. What if you see something, and this is a lot to look at. So let's just focus your eyes right up here. 5 raised to the power log base 5 of 25. How are you supposed to evaluate that? Well, it's an exponent. It's a base raised to an exponent. So first thing I do, with all of these, set them equal to x. Now, if I'm in exponent form, the way I undo that is to write it in log form. So we are going to do that. First thing I did was I have 5 to the log base 25. I said set it equal to x. Now I have a base raised to an exponent that equals an argument. So we're going to go ahead now and write this in log form. And remember, if you, again, look at your 7.3 notes, if you don't remember how to do that. But what we have is we write the word log. There's our base. Our argument now goes right in on this side of the equation. And the exponent, which was a very weird log base 5 of 25, gets its own side of the equation. Now take a look just for a second at this. You've got a log, you got a log. Got a base 5, base 5. You got an x, you got a 25. Reason it out. What does x equal? You said 25, you're exactly right. So we can simplify these expressions. When you see something like this coming through on your homework or in some sort of an equation with an exponent or with a base raised to the log of that same base and then another argument, we can simplify that down just to the argument 25. Let's take a look at another one. Suppose I have 15 raised to log base 15 of 3. Now we could certainly write log, set it equal to x and both write, log base 15 of 3 and so on, and do what we just did there. Or here's a simplified way. What you'll see most math teachers do is they cross off the 15 and the log 15 and just leave the 3. And that's what it equals. So this is the proof. The proof of why that works is right here. But from now on, when we see something like this, we're just going to cross off. If it's a base raised to the log of the same base, we're going to cross those off and just say it equals that argument right there that was in the exponent. Take a look at that. You're going to see that actually not a lot, but enough that it's worth memorizing that or knowing that concept. Okay, here we go. Expanding logarithms. Now, here we go. I've got log base 4 of x squared. How can you expand that? Nothing's multiplied together or divided within the parentheses. So what I'm going to do is I've got an exponent there. That's about the only thing I can do. So I can take that exponent and bring it down in front. And I do that. So that 2 that was right up there comes down in front of the word log. 2 log base 4 of x. That's as expanded as that gets. You can't do anything else with it. That's all you can do with it. Let's try another one. Log base 2 of 4x squared. Well, I've got an exponent, but the exponent only applies to the x. It doesn't apply to the 4. So I don't want to bring it down in front of this because then it'll make it apply to the whole thing. When you if the exponent was outside the parentheses, if it was sitting outside here, then I absolutely would bring it down front. But it's tucked inside and it's only applying to the x, not the 4. So I am actually going to split apart these two quantities that are multiplied. Go back and look at product property. We ran it one way. We said we had 2 logs that were added. We combined them to a single one by multiplying the argument. In this case, I have an argument that's multiplied. I'm going to break it, expand it into 2 separate logs by using addition. So this becomes log base 2 of that 4 right there, becomes that 4 right there. And this x squared right here becomes this x squared right here. I split apart the argument. I broke it into 2 pieces. Now, we're not done yet. Let's take a look at what else we can do. Some of you can spot one of them. There's 2 more things that need to be done with this. See if you can spot one of them. How about log base 2 of 4? Take a look. What exponent can I put on 2 to make it equal 4? If you can reason one out, that can be simplified. I wrote it over here. I said log base 2 of 4, put it equal to x. And I went into exponent form. 2 to the x power equals 4. When you look at it like this, it's much, it's much easier to see. This will simplify down to 2. And indeed it does. This one, has the square now just on the x, and that came down in front right here. So this little 2 that was up on the x squared, that squared now comes down, and it just applies to this part of the log. It didn't apply to this one. So this simplified expression is 2 from this part, plus that 2 brought down front, so 2 logs base 2 of x. Okay, lots of details in these. Let's keep going. Here's one that's divided. I've got a log base 4 of x squared over y. And again, note that the square is only on the x, it's not on the y. What am I going to do with this? Go back, think about your quotient property. Now, when we had quotient property, we had 2 logs that were subtracted, and we combined them into a single log that was then the first expression divided by the second expression. We're going to do that same thing backwards right here. I'm going to take log base 4, my top expression, x squared, minus log base 4, my bottom one, right there. So when you're dividing, you can split it into 2 quantities. Now, you still can simplify, though. You have an exponent, so this 2 needs to come out front. And indeed it does. I cannot simplify the log expressions beyond that, so that's as simplified, or I'm sorry, as expanded as that gets. Now, let's evaluate some logarithms. We're going to use the properties that we talked about. We're going to simplify and see what we come up with. Now, first thing I notice, same base. So I can simplify these down to a single log expression. Second thing I notice, minus sign. Means I can use that quotient property and combine them to a single log expression, top divided by bottom. So let's go ahead and do that. I've got log base 2, same base, base 2, top 6 divided by bottom 3. That gives me the log base 2 of 2. Take a look at that. What exponent can I put on 2 to make it equal 2? Well, if you weren't sure, you could certainly write this as log base 2 of 2 equals x. We're going to simplify this part again. Put it into exponent form. 2 to the x equals 2. So x equals 1. Let's try another one of those. How about this one? Log base 4 of 2 plus log base 4 of 32. Okay, First thing I notice, same bases, so I can combine them. It's a plus. That means you multiply the arguments to bring them together in a single log expression. So this becomes log base 4 of 2 times 32. So I took this 2 and that 32, and I multiplied them together. That becomes log base 4 of 64. Now you've combined it to a single log expression. So definite get points for that. But take a look at this. Can you simplify this even more? Remember, log says, hey, when you see the word log, it says, what exponent can I put on this base 4 to make it equal 64? Is there one that's an integer that we know? Well, write it this way. Maybe this helps. Log base 4 of 64 equals x. Now go into exponent form. Base to the exponent equals the argument. So 4 to the x equals 64. Now go back running through your brain. 4 times 4 is 16 times 4 again, 64. So 3 4s, 4 times 4 times 4, 64. So your answer, that whole thing simplifies down to 3. Here's a weird one. Log 5 plus log 20. There's no base written down. There's no base written down. What do I do if there's no base written down? Yeah, you guys got it. Log base 10. So there should, if you want to squish a 10 in there and a 10 in there, go ahead. Now, plus sign. That means if they have the same base, you can multiply those two arguments to combine them down to a single log expression. So I did that. So this is log of 5 times 20. I put the 10 in there just in case you want to see it. If it helps you, use it. And 5 times 20 is 100. Before we go racing off to the next problem, take a look. What exponent can I put on 10 to make it equal 100? If you can think of one, you got to solve it. Now, I write it like this. Log base 10 of 100 equals x, so that I can go into exponent form. I'm going to take that 10, the base, to the exponent, x, equals the argument, 100. There it is. When you see it like this, I think it's much easier to see. I think you guys can solve this with no trouble. This up here is a lot harder to see, that it's asking for the same thing. These two things are asking the exact same question. And there is one, obviously, is 2. So this takes some getting used to. If you're a little frustrated, like, how am I going to see that? I'm not going to see that. Don't worry about it. You'll get, it's like riding a bicycle. It just takes a while, and it's wobbly, and you fall a lot. And then, you know what? We'll pick you back up, and we'll keep you going. We're just practicing this, getting you guys used to this. Okay, now, one more for you guys. Look back through your notes. I've got a base raised to a log of the same base. What does this equal? This one is like a no-brainer. Draw a line through some things. If you did that and said it equals 1, you got it. If you are not sure why that is, go ahead. I'm looking back up through my slides here to figure out which slide it was. Was it slide 8? Yes, it was slide 8 that explains it. So if you did not like that and you don't trust that and think that's a little too weird for words, go back up, look at slide 8 again. Okay, we're going to keep going on though, folks. Now, we're going to come up with things that are very strange. 64 raised to some power equals 16. If I put a 1 in here, I'm already at 64. So I obviously have to be smaller than 1. So just by inspection, I know that I'm going to have some sort of weird fractional exponent. So how do I solve this? First way I like to try is to find a base that is the same for both sides of the equation. Think about 64 and 16. Do they share a base? Well, you could use 2, because 2 times 2 times 2 times 2 times 2 times 2 is 64. 2 to the 6th is 64. And 2 to the 4th is 16. We played with this a little bit when we were doing exponent stuff in chapter 6. I like to use 4 because it's a bigger number, less work. So I know that 4, we just played with this a little bit earlier in this presentation. 4 cubed is 64 and 4 squared is 16. I think we've seen both of those. So I replace these numbers with their common base. I replace 64 with 4 cubed. I replace 16 with 4 squared so that the bases are exactly the same. Now, remember your exponent rules. A power raised to another power, what do? You multiply. So 4 raised to third power raised to the x is 4 to the 3x. Now, take a moment and just look at, let me see if I can find my highlighter. at this equation for me right now. Just look at that. Notice that the bases are exactly the same. So what do we know about those two exponents? Yeah, they have to be equal. The 3x has to equal 2 in order for this equality to hold. So just write that part down. The 4's can just go away. They're exactly the same. So we're going to let those drop out. We're say 3x equals 2, and then just solve for x. So finding a common base for these can be really powerful. Let's go ahead and we are going to do a change of base formula. I thought I had another example for you. I think I must have deleted it because I'm looking at time. So we're going to go ahead and we're going to use that same idea. We're going to solve some that way on the homework, but let's keep going on, and we're going to find a way to solve even if we can't get the bases to be the same number. Now, big important formula. Note this one. Log base b of some number m or some expression m. You can find a totally different base. If these two don't play well together, go find one that plays well with them. There's a completely different base c. You can take the log base c of whatever your argument was and divide it by log that same base of whatever the original base was, and you can solve these. So we can pick the base that we want. If there's not one like what we had back here where they were both had, this one was nice because they had 2 or 4. We could have used either base to solve. Well, what if you have some that you don't have a common base for them? Let's take a look. For example, log base 4 of 8. I cannot put an exponent on 4 and turn it into an 8. So what I can do is I can say, hey, 4 and 8 are both numbers that are base 2. 2 squared is 4, 2 cubed is 8. So let's use 2. So I take log base 2 of my argument 8 over log base 2 of my base 4. Now this gives you 2 logs to solve instead of 1. So now you've got to do twice the thinking on these. So what exponent do I put on 2 to equal 8? That's what a log is asking. It's just asking what exponent do I put on my base to get this number? I put a 3 on it. 2 cubed equals 8. Down below it, here, what exponent do I put on 2 to make it equal 4? Well, 2 times to the squared power, 2 squared is 4. So 2. Let's do another change of base one. Let's try log base 9 of 27. I know these two numbers will play well together, but I can't multiply 9 by something to get it to 27. So let's go ahead. These are both numbers that are base 3. So I'm going to use that as my chosen base. And I'm going to say I'm going to take log base 3 of the argument 27 over log base 3 of my former base, which was 9. So the big number goes on top, the little number goes on the bottom. That's how I remember it. Now, each of these we can solve. What exponent do I put on 3 to make it equal 27? Well, 3 times 3 is 9 times 3 is 27, so 3. And then what exponent do I put on 3 to make it equal 2? You put a 2 on it. So 3 squared is 9. Now, this one's a little bit weirder because you knew I was going to make it weirder. It wasn't weird enough. Log base 2 of 32 to the 5th power. Okay, first of all, you got an exponent right there. So you're going to have to deal with that first. I bring it out front. Remember, our power rule says when you have an exponent on the argument, send it out front. So here's that 5 right here, sitting right here. Oops, there's my highlighter. This 5 and this 5 got right there. So I'm going to have now 5 times whatever quantity this is. Now, some of you might go, hey, log base 32, log base 2 of 32, that's 2 times 2 times 2 times 2 times 2 is just 5. But if you didn't see that right off the bat, or you want to use a change of base formula, go ahead. We know these are, you got a base 2 right there. So we know log base 2 of 2. We've done that several times now. We know that equals 1 when the base and the argument are the same number. So then log base 2 of 32, we go ahead and we say, hey, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I know this top part here is 5, And this bottom part here is 1. And there you go. Now, don't forget to multiply that times the original 5 to get 25. Okay, now can you pick any base you want? Well, yes and no. I mean, a common base is easiest and the fastest by far. So here's another example that uses a common base. I have log base 8 of 32. Again, we both know we've just done some examples with this. I did one with an 8 and a 32 in the previous slide. So we know that 2 is a common base for both of those. So let's take log base 2 of 32 and put that over log base 2 of 8. So what exponent would I put on 8 to make it equal 32, which is what this expression is asking? Well, I use my change of base formula right here, and I find out this is a 5, and the denominator is 3. So 8 raised to the 5/3 power would equal 32. So these are how you start to solve or simplify some of the more complicated log expressions. What, though, do you do if you can't figure out what base to use? And this is where you go grab your calculator. Anything from a scientific or graphing calculator on up will have a key that says LOG. And this is a base 10 log. So for example, suppose I gave you this problem, log base 2 of 27. Well, 2 and 27 do not share a common base. One's odd, one's even. That's a kind of a giveaway right there. So we're going to use our common base, base 10, and take the log base 10 of 27. Notice I didn't bother to write in the 10 over log base 10 of 2. Then I'm going to grab my calculator. I'm going to make it do the work. So I'm going to hit log, enter the 27, close parentheses, and I get about 1.4 and some change. And do the same thing with log 2. Now, when you divide these, if you don't close your parenthesis here, hit the divide key and then open a new parenthesis for the word log, you will get some strange things happening on your calculator. So with calculators, it will start to take the log of something weird dividing. I've had so many strange things happen for students. So practice a few times with the calculator that you're using. Make sure you understand how to use a change of base formula. Some calculators actually have built-in change of base formulas. You can put it right into the calculator. I think some of the TIs do. I'm not sure though. I find it just as fast and easy. I never can remember how to do this on my calculator. So I just find it as fast and easy to use the change of base formula. But do make sure, try this. Grab your calculator, try this a couple times. Make sure you're matching my answer. If not, you're forgetting an end parenthesis here divided by open parenthesis here, log 2, close parenthesis, enter. And I think that should get you there. One more I want you to try with your calculator so you get it. Log base 3 of 16. No way to pick a common base for these. So we're going to use base 10. Log base 10 of 16 over log base 10 of 3. Grab my calculator, hit the log button, put in a 16, end parenthesis, divided by open parenthesis, log 3, close parenthesis. Probably have to hit close parenthesis a couple times actually. You should get the matching answer here. If you don't, shoot me an email or something and I can help you debug what's going on with your calculator. So this is a super powerful way to evaluate log expressions. Okay, there are going to be some worksheets in Canvas for you to take a look at, to practice with. There'll be the Canvas quiz. If you have questions, hit up our office hours, email your teacher, any of that works. We hope you all are doing well and really appreciating you spending the time on the math. Thanks.